Our next speaker is John Dickol from Samsung. He's the principal engineer at the Samsung Austin Research and Design Center in Texas, where he's currently developing verification tools and methodologies for GPU and CPU projects, and looking for new ways to apply system Verilog constraints. Before joining SARC, he led verification teams for SOC and DSP projects at MediaTek, Analog Devices, Intel, and IBM. John has a Bachelor in Electrical Engineering from Lehigh University and a Master's in Electrical Engineering from Syracuse University, and has 5 US patents. Over to you, John.
Okay, thank you, Sarah. So today I'm going to talk about one of my favorite topics, system Verilog constraints. And I'm finding that I can do all kinds of creative things with them, which is kind of what led to the title of this talk. I was showing a colleague some of the work I had done with constraints, and he was kind of baffled or surprised that constraints could actually do something as complex as that. So today I'm going to talk about some of the techniques we have in system Verilog constraints that can be used, and I'll show an example of how you can apply the constraint language to some fairly complicated problems. So over the past several years, the system Verilog constraint solvers have gotten better and better, and they can handle more and more complex problems. And why would you want to do complex constraint problems? Well, a good rule of thumb is I use constraints to define legal stimulus, legal random stimulus, and then you can layer constraints on top of that legal definition to kind of steer your stimulus towards specific corner cases that you're trying to cover. And if you have a complicated stimulus you're trying to generate, you need complicated constraints in order to model that appropriately. So we'll start off with a review of some of the newer or perhaps lesser known constraint techniques that are available. But before doing that, let's just do a quick review of constraints in general. Number one, system Verilog constraints are declarative. They're not procedural. What you do is you describe to the constraint solver what you want, the type of result you want, and the solver figures out how to implement that by choosing random variables appropriately. Constraints are nothing more than system Verilog expressions which must be true. And these can be any valid system Verilog expression using variables or constants of integral type, and that's an important distinction. You can't, at least not yet, do floating point constraints. And the constraint solver will choose values for all of your random variables, ensuring that all the constraints are satisfied. And one thing that sometimes throws people off is all these constraints are solved simultaneously. It's not like you're solving, constraint A and then constraint B. Everything's happening all at once. Now there are some exceptions to that. You can control the order of the solving, but for the most part, it's a set of simultaneous equations that are being solved. The full specification for the constraint language, your best references go to the system Verilog language reference, IEEE standard. The one I used when I developed this talk was the 2012 version, but in the interim, there's a 2017 version I'm not sure if it's released yet, but it should be soon, should be available. And at one point, you could download a free copy from IEEE. That link for the 2012 version seems to be invalid, and I'm hoping that in the next weeks or months, you'll be able to download the 2017 version in a similar manner. So stay tuned. So let's start by just quickly looking at some types of constraint expressions that are available. They can range from very simple to very complex. I mean, this right here is a valid constraint expression. It's not a very interesting constraint expression, but it is a valid one nonetheless. It's always true. This one is always false. There are probably very few cases where you'd want to use these types of expressions. Now you can do simple equalities, constrain x to equal 1, or inside a range of values, here x between 0 and 10. X can be less than y. You can have arbitrarily complex expressions here. Here the sum of x and y must equal z. Conditionals. Here's a case where a rather complicated way of saying x not equal y. If x equals y, then 0 or false. So it's, again, kind of a convoluted way of writing it, but it is a legal constraint expression nonetheless. Now, on the more complex end of the spectrum, we can do things like this. I won't explain it here, but one of the examples I show later in the talk will explain what this constraint expression does. And here's another example, another single constraint expression from one of the other examples. So the first technique we want to talk about is soft constraints. And these, I believe, showed up in the language in the 2012 version. And what they are constraints that are only applied if they're not contradicted by other constraints that have a higher priority. And there's a fairly elaborate description in the LRM of what the constraint priorities are. But in general, the last constraint specified is the one that has the highest priority. And see the LRM for a complete list of those. And where I've found soft constraints useful is if I wanted to specify a default value for like a UVM sequence or sequence item variable, but I want to be able to override that when I instantiate that sequence in a higher level sequence. And here's a simple example of that. I have a kind of somewhat trivial UVM sequence that I've defined, and in here I have a soft constraint for the count variable. So by default, count will be between 10 and 20. Now I can derive another sequence from that. And in that sequence, if I were to just use a UVM do macro to run the original sequence, the default constraint applies and I'll get a count between 10 and 20. What I can do though is I can add a with constraint to my randomize call. So now I'm saying run the same sequence, but let's make sure that the count equals 1000. Which will override the 10 to 20 default, because if I had both of those constraints and they were not soft constraints, the count cannot be both between 10 and 20 and also equal to 1000. I would get a constraint solver failure. So by having the soft constraint on the default, I can override that. Unique constraints are another interesting one. I haven't found too many uses for these, but what a unique constraint will do is constrain a set of variables to have unique values. And this can be a list of scalar integer variables. It can be an array of integer variables or any combination of those. So here's a simple example, just kind of illustrating some of the ways this can be used. I have a couple of random variables and an array, a random array, and a non-random queue. And I can say X, Y, Z are unique, and none of them are equal to the other. I could have written it as a series of inequality constraints, but unique is so much easier to do that. I can also randomize the contents of an array and ensure that all of those are unique values. I can mix variables and arrays. So here X, Y, and the contents of the array will all be unique. Here I can pick X and Y such that they are not equal to any of the values in the queue. So there's a whole, many combinations of these things you can use. Another really powerful technique is array constraints. And there's a couple of ways you can iterate over the contents of an array. The most common one is, that people probably are familiar with, is the for each constraint. And that allows you to very compactly write constraints that apply to every element of an array. You can also constrain the size of an array. But if you do that, it's according to the language reference manual, the array size will have to be solved before any of the iterative constraints for the individual elements. Here's an example of what that might look like. Here I'm using a for each loop to constrain each element of the array to be between 0 and 15. Here I'm constraining the size of the queue to be between 5 and 10, and then for each element of the queue, create a sorted queue, ensure that each element is greater than the previous element. This is not the most efficient way of sorting a queue, but it serves to illustrate how you can use a for each constraint. And note that here I have what's called a constraint guard expression, where there is no, the array indices range from 0 to whatever the max number is. So my constraint expression using I minus 1 would attempt to reference an element not in the array. So by putting this, what's called a constraint guard, if I is greater than 0, then apply the Q of I is greater than Q of I minus 1 constraint. Otherwise, you'd get an array out of bounds error. Another flavor of array constraints is what's called reduction constraints. And these operate on unpacked arrays of integral values. And what they do is they apply a specific operation between each element of the array. Here's a simple example. I can sum the elements of an array, and I can just write a dot sum, and that will be equivalent to a of 0 plus a of 1 plus dot dot dot, no matter how many elements are in the array. It'll generate the constraint appropriately. But I can do more than just sum. There's several other methods that are predefined. There's product and, logical or, and I'm sorry, bitwise and, bitwise or, and bitwise exclusive or are all available. I've not had a chance to use most of these. Sum and or are probably the ones that I've found the most uses for, but you may find ways to apply these other ones. One thing to keep in mind is these array reduction methods return a single value that's the same type as the array element. So if I have an array of int variables, the sum returns an int. If I have an array of single bit variables, I get a single bit result. Now this can cause trouble if I'm trying to sum an array of bits. I can't put a 10-bit result in a 1-bit result expression. So what the language makes available is what's called a with expression. And this is kind of analogous to the randomized with expression, but here it's applied to the array reduction operation. And that with expression is applied to each element of the array before the reduction operation takes place. So before doing the sum or the exclusive or, apply this expression. And we have an example of that on the subsequent page. And within that with expression, there's a couple of magic variables. One of them is called item, which refers to the current array element. And the other one is item.index, which refers to the index of that current array element. So let's look at how this works in some examples. Right here, I want to constrain the number of ones in an array of bits. And in this case, it looks like I want to create a bit, let's see, a queue of bits that has between 10 and 20 entries. And I want the number of 1 entries to equal 7. You can see here that what I'm doing is I'm casting the item variable to be an integer, because otherwise I would try to sum up a series of single bits and get a 1-bit result. I'd get overflows. By casting item to an int, I get a 32-bit result, so I can easily contain the sum of my queue entries in that integer result. Here's a little more elaborate example. I want to sum up just the first 3 elements of an array. All right, so I can use the sum with expression again, and here I'm using the item.index variable so if the index of the array element I'm summing is less than 3, then I want to add the item, the value of the array. Otherwise, I want to add 0. Then I want the sum of those first 3 elements to be equal to 10. It's a somewhat contrived example, but it kind of illustrates how you might use this technique. And here we have the item is equivalent to the array element itself, a of I, and then item.index is equivalent to I in my iteration expression. Another cool trick we can apply is what's called global constraints. The language reference calls them global, but I think a better name would be hierarchical constraints. And what this lets me do is I can have if I have a class that has random variables in it, that class can be a random member of another class. So I can have a hierarchy of random classes and random variables. And when I randomize the top level object, all the random variables and all the classes in the hierarchy get randomized at once. Single randomized call randomizes everything. And what this lets me do is apply constraints from the top level to lower level objects. So an example of this is a somewhat made-up example, but let's pretend we have a very trivial line drawing application that can draw horizontal lines and vertical lines. To draw a line, I need 2 points, so we'll start with a class that has 2 x and y coordinates in it. There are 2 random variables, and I'm limiting them to be between 0 and 100 are the coordinates. Now what I can do is create a line class which instantiates 2 of those point classes. Those 2 points are declared as rand. I also have a random direction which can be horizontal or vertical. And what I can do is write constraints in the line class that apply to the individual point coordinates. So if I'm drawing a vertical line, I constrain the x coordinates of the 2 points to be equal. And if I'm drawing a horizontal line, I will constrain the y coordinates to be equal. Another useful trick is we may want to reuse constraints. So if I want to, define them one time and use them in multiple objects, you can use inheritance, but that can get cumbersome if you're trying to combine multiple sets of constraints in multiple ways. You can also want to add additional constraints to an object at runtime. You may not know in advance what constraints you want, so maybe there's some command line controls or some other testbench state decides what constraints you want to enable or add. And what this technique lets us do is package constraints in a container class, right? So, and it's kind of a variation of the hierarchical or global constraints we just talked about. The difference here is the lower level object can constrain the parent object. We kind of turned it around and reversed it a bit. And what we do is define what I call a policy class container. And I specify my constraints in that class, and they apply to the upper level. And there's a common base class that these are all derived from, and we'll see an example of this coming up. And here I've stolen the item variable from the width expression for the array reduction. I'm using that same idea. So the policy class can use the quote item variable to refer to the parent object. And inside my parent object, I can have one or more of these policy classes. I've chosen to use a queue in this example, but we'll see how that works. Now, there was a DVCon paper, looks like 3 years ago, that I wrote about this. So if you want to learn more about this technique, you can look up this paper. So let's look at this in more detail. And this is all, I apologize in advance, this is a somewhat busy slide. So here's our line drawing class from the previous example. And one thing that's different is now there's this random queue of policy base items in it. And okay, what is that? Well, let's take a look. It's a base class, doesn't have a whole lot in it. There's this item variable that's declared, and there's a function called setItem. But so this class by itself is not very interesting, but what we can do is derive a class from that. Right, so here's our line direction class, for example. And what I'm doing is writing constraints in here. I'm using the item variable to refer to the direction variable in the parent class, right? So I'm writing my constraints using item dot whatever, and there's some secret sauce that will ensure that item is set to point to the proper object. To actually use that, here's a simple test case that instantiates the line object. It instantiates the line direction policy class, adds it to the queue, and then when I randomize the line object, well, the pre-randomized method is going to go through and iterate through all of the policy classes, call this setItem function, which is going to set the item variable in the policy to equal the class handle for the object being randomized. A little convoluted, but follow the arrows and it'll make sense. And again, see the DVCon paper, which describes the technique in much more detail than I have here, than I have time for today. So now that we have a toolbox of techniques we can use. Let's look at an example, right? So first example, simple bus interconnect testbench. This is actually something I did at a previous employer a couple of years ago, something very similar to this. We have a bus fabric. It has a series number of masters, number of slaves, and I want to be able to do different types of test scenarios. And here's a list of some of the things we may want to be able to do. I may want to control the total number of transactions in my simulation, or the total number of transactions for all the masters. I may want to divvy up the transactions, so many transactions for each master, or so many for each slave. I may want to ignore one of the masters or ignore one of the slaves, et cetera, et cetera, et cetera. All kinds of combinations. If we create a suitable constraint model for this problem, we can easily add constraints on top of that to implement any of these test scenarios that we're desiring. So how do we do that? So the key is always to create the right data model. For this particular problem, what I've created is a two-dimensional array that maps the number of transactions from each master to each slave. So imagine the rows of the array are the masters and the columns are the slaves. And here I have a example showing, for one randomization of this example, from each master to each slave, how many transactions are sent, right? So for master 0, we see we have 2 transactions sent to slave 0. We have 17 transactions sent to slave 3, etc. So what we can do now is, with this basic model, we can add additional random variables and constraints to give us some control knobs that the test writer can manipulate in order to steer the stimulus in the direction they want to go. Right, so the first thing we can do is, to get the number of transactions per master, we can sum up the rows of the array. Right, so I have 289 transactions for master 0 and 286 for master 3, etc. And I have none for master 4 for some reason. I can sum the columns in a similar manner to get the number of transactions for each slave. And I can sum the entire array to get the total number of transactions for my simulation. So how do we implement this? Well, to get the total number of transactions is actually quite simple. Our old friend, the sum method, can be used. And what's nice about that method is it also works for multi-dimensional arrays. So the fact that I have a 2D array doesn't matter. I just have to call this sum method once, and I get the sum of all the transactions in my array. And that's kind of equivalent to this for each loop I have up here. To constrain the number of transactions for each master, well, I can just sum the transactions in each row. And that's not too much more difficult. I can iterate over each row using a for each loop, and then use the sum method again to sum each of the rows. Doing the transactions per slave is a little more involved because I need to sum the columns, not the rows of the array. So here I have a little more complicated expression, which may look familiar. It's one of the ones I showed on the introduction slide. And what this is doing is iterating over the slave dimension, the column dimension, and it is applying this somewhat elaborate expression to, if the index is equal to the one we're trying to sum up, we add its value to the sum, otherwise we add 0. And another interesting feature for the item.index function is that I can pass a dimension to it. So the fact that I'm saying item index 2 means I'm looking for the second array dimension. And if I wanted to constrain, use or not use some of the individual masters or slaves, we can do what's shown in this example, right? So a master is used if it has at least one transaction. So what I can do is sum up the number of transactions, or if the number of transactions per master is greater than 0, then I indicate that I'm using that master. And if I want to use a particular number of masters, well, I just have to sum up the number of used masters, again, using our old friend, the sum method. And ditto for the slaves. It's same code, just different different dimensions. And so now that we have this constraint model, right, we can constrain the number of transactions per master per slave. We can control whether we use certain masters or not. Now we can write a test scenario that will steer the stimulus towards what we're trying to do in any particular test. And so here's a simple test configuration object, which has our data array plus the constraints. And here I can constrain the total number of transactions to be 10,000. I can say use between 2 and 4 masters, use master 1, but don't use slave 3. But it's writing these constraints. And the solver will figure out all the permutations and give me some random scenario that satisfies these criteria. Now, writing inline system Verilog code to control these scenarios is good, but frequently users want to be able to control these types of constraints from the command line. They don't want to have to write new system Verilog code and recompile the model every time they want to tweak the number of transactions. So there are some techniques we can use to add command line control to some of these constraints. All right, so here's an example where I wrote a function called get plus args, and what that will do is, for this case, for the total number of transactions, if that option is specified on the command line, we'll then grab the number of total transactions and at the same time disable randomization for that variable by setting its rand mode to 0. So now I've pinned the total number of transactions to a specific value. All the other variables are still free to be randomized as needed, but this particular one has a fixed value and will not be randomized. We can do the same thing for the array types of elements. So for using master 1, master 2, etc., what I can do is write a for each loop, which will procedurally compute the option name, the plus arg name, and then use the same technique. If that particular option is specified on the command line, grab the value and set the randomization to 0. And here's how I would use that in my test case. I would just, create my new test configuration, call this function, do my randomization, and then the command line might look something like this. I can, without recompiling my design, my test bench, I can specify constraints like this on the command line. Now you'll notice that I had to quote this particular one because these square brackets would likely be special characters in the shell. So I need to quote it to ensure that this literal string is passed through to the simulator. There was a second example in this talk is derived from a longer presentation I gave a while ago. There wasn't time today to cover the second example, but I did put the slides for that in the appendix, so feel free to look at that. So in summary, what we've talked about today is some different constraint techniques. Some of the newer features that System Verilog provides, or newer or maybe lesser known features, I should say. We talked about soft constraints, which can be overridden, and we talked about unique constraints. Array constraints, one of my favorites, both for each loops and the array reduction functions, sum, product, etc. We talked about a way of putting constraints into reusable containers, and then we showed an example of how to use those techniques. So in summary, basically the constraint solver can handle some fairly complex problems. So go ahead and use it, try it. Make sure, see if you can, what kind of complex problems you can solve using it.